Okay, so features of graphs and piecewise functions. We've been talking about graphs a little bit. We want to talk a little bit about what they, how to describe features of graphs, and then we also want to talk about piecewise functions. So we'll start off with features of graph: increasing, decreasing, maximums, minimums, even and odd, and then piecewise functions. So here's our graph of high and low temperatures for February 2021. What is the story the graphs are telling? So if we look at the high temperature, oh, there it is. The high temperature graph, what's it telling us? Well, remember that we're starting at January 31. So what the high temperatures do is they sit around 30 degrees until, let's see, 1, 2, 3, 4, February 4th. That's here, right? So around 30 degrees. And then it drops, right? And it drops pretty dramatically to about February 5th. Drops sharply on February 5th. That's this part here. And then it hovers between 0 and 10 degrees pretty much until, let's see, 15, 16, 17. And then what happens? The temperature rises up to about 40. By the time you get to here, right? So from the 17th up to 21, 22. And then it just sticks around 40. So hovers around 40 degrees. And so that's a story, 40 degrees, of the high temperatures in February 2021. So we have a period where the temperatures were kind of constant, a period of decrease, a little bit of oscillations between 0 and 10, an increase, and constant again. And these are features that we want to be able to see on a graph and be able to talk about. So increasing, decreasing, and constant, we can actually identify intervals. So decreasing, starting on day 0 and going to day 2, temperatures went down. From day 2 to day 3, they went up. So increasing, and we're using interval notation. Day 2 to day 3, they went up. Then day 3 all the way down, day 5, day 6, day 7. So the interval from day 3 to day 7, it was decreasing. So from here to here to here to here, day 3, day 4, day 5, day 5, 6, 7. So when we're talking about decreasing of the function, we identify it with the x values, the horizontal values, right? From 3 to 7, the function was decreasing. It was increasing then from 7, 8, 9. And then actually constant for 2 days, right? Days 9 and 10. And then it decreased again, 10, 11, 12. Let's see, 10, 11, 12. Decreased again from 10 to 12. And then we have this really tedious little bump. I'm just going to say that it was constant from 12 to 14. And to join separate intervals, right, you use the union sign. And then from 14, 15, 16, it increased again. Decreased for a day. And then increased up every day, went up from, this is day 17 to day 22. And then it did some more stuff. So when we're talking about intervals of increase, right, we're talking about intervals on the x-axis. From day 17 to day 22, the temperature increased. We read graphs going from left to right. And we actually have from day 3 to day 7, that's from here to here, the temperature decreased, the high temperatures decreased. And we're going to have constant periods like we did here. So interval notation, using a union to join separate intervals. Note that every time we go from increasing to decreasing, we hit a maximum. Right? So day 16 is a maximum, right? Day 22, we went from increasing to decreasing. So day 22 is also a maximum. The maximum, absolute maximum of the whole graph is out here, right? Day 27, that's the highest it gets anywhere. But every time you switch from increasing to decreasing, right, you get a maximum. And that's the gaps in between, right? From here to here, at day 3, you actually hit the maximum. You increased, and then you decreased. Likewise, minimums are where you go from decreasing to increasing. So day 7, you decreased into day 7 and increased out of it. So day 7 is a minimum, right? Day 17 is also a minimum because you decreased into it and increased out of it. So a minimum is anywhere where you decrease into it and increase out of it. The absolute minimum is the absolute bottom, and that actually happens for the high temperatures once here, and once here. So there's 3 absolute bottoms. But anytime you go down and then back up, that's going to be minimum. If you go up and then back down, that's the maximum. And the last thing we want to know is where is the temperature positive? So this is the temperature equals 0 line. So right along this line, temperature equals 0. Above the line, temperature is positive. Below the line, temperature is negative. Exactly 0, that's your x-intercepts. So between the x-intercepts, either you're positive or you're negative. So where are intervals that it's positive? Well, at day 15, we've got an x-intercept. And so from 15 all the way out to 28, the temperature was above the x-axis. So that means it was positive. Between, this is the 11th to the 15th, the temperature was below 0, right? And so the temperature is negative. And again, we want to look at these by indicating intervals on the x-axis. So the temperature was positive from day 15 all the way to the end. That would be 15 to 28. And the temperature was always positive from the beginning, which was -1, all the way up to day 6.5, which is somewhere in the middle there. Right? And then it's positive again, I don't know, day 7.5 to day 11. In between those times, it had to have been negative, right? So from 6.5 to 7.5, temperature was below 0. And then from 11 up to 15, that's here to here, the temperature was also negative. And so what happens at the x-intercepts? Well, 6.5 was where we changed from positive to negative. .5 is where we changed from negative to positive. And 11 is where we changed from positive back down to negative. And then 15 is we changed from negative back to positive. And so those must be places where temperatures were 0. Those are x-intercepts. And you can do the same sort of analysis for the cold temperatures, right? The cold temperatures are negative from here. The low temperatures were negative from here to here. And positive out here. Low temperatures were decreasing from T equals 0 all the way down to T equals 7. But they increased a little bit, decrease, increase, decrease, big increase, decrease, and kept going over. So when we think about graphs, we want to know, is it increasing or decreasing or constant as we go from left to right? Maximums are where you change from going from increasing to decreasing. Minimums, you go from decreasing to increasing. Positive, that's where the graph is above the x-axis. Negative is where it's below the x-axis. X-intercepts is where the graph is 0. And so here's the language about all that. It's essentially what I just said. Okay, so even and odd symmetry. These are two graphs, and they have a certain type of symmetry about them. This graph is symmetric over the y-axis. Symmetric over y-axis. And what does that mean? That means if I pick any point here, I'll say this one, that's at a particular x value, right? Say x equals 3. Then if I look over on the other side of the graph, I get exactly the same point, just flipped over there, so at -3. So it's the same height, right? But one's a plus, one's a minus. So the symmetric over the y-axis, the left and right sides look the same. This is a graph that's called symmetric over the origin. Right? That means if I take a point, say like 2.5, that's this point. So we'll say this is x is 2.5 and y is 5, 6, 7, 8, and no, 8.5. We can draw a line that connects it to the origin. If we take this line and just run it through the origin for the same length on the other side, we'll get to the same point, but with the coordinates reversed. Now we're at y equals -8.5, x equals -2.5. Right? So if I take these 2 points on the graph and draw the line that connects them, the midpoint of that line is directly at the origin. That means that we put a minus sign on our coordinates, and that gives us the other point. So that's what symmetric over the origin means. Okay. So symmetric over the y-axis, symmetric about the origin. This one is called even. And this one is called odd. And we'll see why those names come about. So from a graph, you can tell if it's even or odd pretty easily because you just sort of look at it and see if it has the correct symmetry. But how can you tell from the formula or a table? Well, we'll set up a table for this one. We'll call this one f of x. And we can set up a little table for that. So x, f of x, and those are my y coordinates. So if I pick an x coordinate, say 1, whoops, didn't want to do that. I just wanted to scroll up. Go. X coordinate 1, that's here. My y coordinate looks like it's about 1.4. If I take x coordinate -1, that also gives me a y coordinate of 1.4. So x coordinate of 1 gives me a y coordinate of 1.4. X coordinate of -1 gives me a y coordinate of 1.4. What about 2? Well, if I take an x coordinate of 2, that gives me a y coordinate of about 2.8, about. And if we have -2, that gives us a y coordinate of 2.8 about. So 2, 2.8, -2, 2.8. So what are we seeing on this table? We could keep doing this, but no matter what x value I pick, if I pick any x value, we'll just say an x value here, if I pick that, I will get a y value of whatever this is, and that's f of x. If I take the equal and opposite x value, so this is minus x, if this is x is about 2.6, this is minus 2.6, and we go all the way up till we hit the graph, we go over to the y-axis to see what we get, that's f of minus x. And those should always be the same, right? And it shows up in the table, equal and opposite x's. So if I take any x, I should get out whatever y value is, I get f of x. And if I take the opposite one, I should get minus y equals f of minus x. And these two things should be equal to each other. So 2 and -2 both give me 2.8, 1 and -1 both give me 1.4. So f of minus x should be equal to f of x. That's a nice little formula. So you can tell if you have a table, as long as you take equal and opposite and you get the same number, that's an even function. If you have a formula, you can just plug in minus x and see if that's the same as you get f of x. How about this one? Well, we just saw that if you take 2.5 and plug it in, you get about 8.5. We'll call this function g of x, just so that we have a label for it. Okay, so x and g of x. We plugged in 2.5 and we plugged in minus 2.5, and we got that the output was 8.5 in one case and minus 8.5 in the other case. So what happens if we take x equals to 1? Well, that gives me an output of -2. If I take x equal to -1, right, equal and opposite to 1, that goes up the other way. So that gives me 2. So 1 would give me -2, but -1 gives me +2. And so what are we getting here? Equal and opposite x's give equal and opposite y's. So what happens if I just pick some random x? So suppose we take x to be, this diagram's a little bit cluttered. We'll take x to be some number in here. Suppose this is x. Right, then the y value that we get for this x is down here. That's my y value. If I flip that, right, I want the corresponding point on the left side to be on the other side of terrible drawing. Minus x should give me a minus y up here. So if I take 2 points on the graph, right, and draw them with a little, connect them with a line segment, the line segment should go through 0 as long as I use equal and opposite x's. So unfortunately, my diagram is gotten a little bit terrible. So we'll try an x out here. Suppose we just pick an x value between 2 and 2.5, and it gives me a y value out here. There's my y value. If I take minus x, which is out here, I go to the graph, what I'll get is the opposite y value. So equal and opposite x values give me equal and opposite y values. So this is equal to f of minus x. This is equal to f of x. Putting these together, y equals f of x. And then whatever y this is, that's better be equal to f of minus x. So together these tell me that the output from minus x is the opposite of what you get for x. So if I plug in the x value and get this y value, if I plug in the opposite x value, I should get the opposite y value. So f of minus 1 is the opposite of what you get when you plug in 1, so that's 2. F of 2 is the y value is the opposite of what you get when you plug in minus 2.5, and so that's 2.5. So again, if you have a table, equal and opposite x's give you equal and opposite y's, that's odd. Neither, well, if neither of these things happen, right? If you plug in equal and opposite numbers and you get random numbers that aren't connected to each other, that'll tell you that it's neither. So there's the procedure. Function is even means this graph is symmetric about the y-axis. Equal and opposite x's in its table produce the same y, or if its equation satisfies that, right? So we have a rule for graphs is symmetry. For tables, equal and opposite x's produce the same y values, and a graph and a statement for the equation. Again, graph, table, equation, 3 ways of thinking about functions. So for these 3 functions, even, odd, or neither, just by using the formulas and not graphing them. So how do we actually go about finding this? To check if something is even, odd, or neither, the first thing you do is calculate with minus x. So we'll start with f of x here. So what we do is say, well, what's f of minus x? That would be minus x quantity to the 5th plus 2 times minus x quantity cubed plus 3 times minus x. What do we know about negative numbers raised to odd powers? They keep their minus signs. So this becomes minus x to the 5th. And then this will be minus x cubed is the same thing as minus quantity x cubed times a 2. So this isn't actually going to be a plus. It'll be a minus 2x cubed. And then 3 times minus x is minus 3x. And now what I've got is I've got something that's common to all 3 terms on my function, f of minus x. I can factor out that minus sign. And I get this. And that's my formula for f of x. Right? So this is an odd function. Why is it called an odd function? Notice that these are all odd powers, right? 3x to the 1st, right? And what happens when you have a negative raised to an odd power? You keep the negative, which means you can factor it all out and you're left with the function again. So g of x, how do we calculate whether or not this is even, odd, or neither? You calculate with minus x. So that gives you 3 minus x to the 4th plus 2 times minus x squared plus 1. What happens when you take a negative number and raise it to an even power? Well, the minus sign goes away. And now we have exactly this function. And so that's an even function. Right, so you plug in minus x into the function and see if you get back exactly the same thing. That's even. Why did that happen? All even powers, right? And a constant. And when you raise something to a negative number to an even power, you end up with the negative sign going away. Now, h of x, you plug in minus x, you end up with minus x quantity to the fourth plus 2 times minus x cubed plus 5. And if you calculate that out, negative x to the fourth, the negative sign drops out. Negative x cubed, you keep the minus sign because it's an odd power. And then you plug in the plus 5. So h of minus x equals, h of x, the original function, just to write that down again, is this function. These two things are not the same, so they're not even, and they're not opposites of each other, so it's not odd. So this is neither even nor odd, and it's got a mixture. Some of the powers is an x to the fourth, that's an even power, an x cubed, that's a negative power, so that's going to be neither even nor odd. So, and just to sort of reinforce this, we can go over to Geogebra again. And Geogebra is a really useful way also to check your work sometimes. So those three functions we were just looking at, one is x to the fifth plus 2x cubed plus 3x plus 3x. And it looks like that. Not a very exciting looking function, but you can see that it's odd. You pick a point on it, equal the, it's reflected about the origin. So this is an odd. You take the right side here and flip it over, and then flip it over the y-axis and then over the x-axis, so you get the left side. And we can do a table of values, right? And note equal and opposite x's give you equal and opposite y's, and also x equals 0 and 0. So odd function. The other function we had was y equals 3x to the fourth plus 2x squared plus 1. And if you graph that, you get this. Also not a particularly exciting looking graph or anything. Actually kind of looks like a parabola. And the left side and the right side match, right? So it's an even function. And we can look at a table for this. Right? And equal and opposite x's. So minus 2 gives you 57, 2 gives you 57. Minus 1 gives you 6, 1 gives you 6. Equal and opposite x's give you the same y value. Good. And the last one was our neither function. And that looks like that. And you can tell that this is neither even nor odd, right? If you swap it left for right, you don't get the same x value, you don't get the same y values, and it's not symmetric over the origin, right? You'd expect if the right side of the graph is in the first quadrant, if it's odd, then the left side of the graph should be down in the third quadrant. And we can insert a table to see what the values look like. And here, minus 2 gives me 5, but plus 2 gives me 37. There's no particular relationship between the y values I get for equal and opposite x's. So it's neither even nor odd. So Geogebra is really, really useful as a calculator. And so, and I think it's free on your phone. So, use it. Okay, so back to the lecture notes. we're going to talk about piecewise function now, and this means that we're going to use more than one expression. So this is a piecewise function. And what it's got is it's got three different formulas, x squared plus 1, minus 3, and x minus 2. And then it's got three different intervals. And the rule is for each input x, you use the appropriate interval. So, oops, didn't want to do that. There we go. What's x of minus 4? If x is minus 4, what's y? Well, minus 4 that's true, right? If we plug in minus 4 in for this x, we get a true statement. So that means you use this formula. And so minus 4 squared is 16 plus 1, so y is 17. Minus 3 is between minus 4 and minus 1. So that means you use this formula for calculating y. And that gives you minus 3 squared plus 1. Minus 3 squared is 9, so 10. Minus 2 is between minus 4 and minus 1. So you use this formula. And minus 2 squared is 4, plus 1 is 5. Minus 1 is one of the endpoints here, and we use the less than or equals there. So we use that formula for minus 1 because minus 1 is in this interval. It's not in this interval because it's a strictly less than. So minus 1 squared is 1, plus 1 is 2. Now 0, if we plug 0 into here, you get minus 4 less than or equal to 0 less than or equal to minus 1. And that's false because 0 is not less than or equal to minus 1. If you plug 0 into this equation, though, this interval, you get minus 1 less than 0 less than or equal to 1. And that's true. So that means we use this formula. And that just tells me that if x is 0, then y is minus 3. So not particularly exciting thing. Likewise, if x is 1, that means you're in this interval because this is a less than or equals. And so we get a minus 3. If x is 2, well, 2 is bigger than 1. So that makes this sentence true. And so we use this formula. And so that gives me 0. And 3 is bigger than 1. And 3 minus 2 is 1. So there's my x's and my y's. Now we can sort of plot points. 17 is sort of up off the top of the chart. 10, minus 3, 10. 3 will be halfway through. Minus 2, 5. Minus 1, 2. 0, minus 3. Let's see, scroll down a little bit. Minus 3 will be down here. 1 minus 3 be here. 2 is 0 and 3 is 1. And now we have to be careful about how we put these things together. So we use the same formula for x's between minus 4 and minus 1. So x's from minus 4 to minus 1 means x's from here to here. And that's this graph. So we can connect these together like that. And this is the graph of y equals x squared plus 1, but only for the x's from minus 4 to 1. Okay. What about the next interval? That's from minus 1 to 1. So x is from here to here, right? They have to use this formula, y equals minus 3. So these two dots, those connect together. That's nice. But we need to fill in the rest from here. The x is all the way out to here. And we go out to here to the left, y equals minus 3, and then an empty circle there, because when x is minus 1, the y value we want is y equals to 2, that's this part, and not y equals to minus 3, which is that part. So this is y equals minus 3, the middle one, but only for x's between minus 1 and 1. And then finally, we have y equals x minus 2, but only for x is bigger than 1. So that's these two. And how far to extend it to the left? Only until we get to that vertical line, because that's when we have to change our formula. And so that'll go back to here, an open circle. And it says x bigger than 1. So we just keep going off to the right. We'll put a little arrow there that says we're continuing off to the right. Note that we actually stopped here at -4. Right? So this is the end of the graph to the left is here, but it goes infinitely off to the right. And so that's what our graph is. We have 3 pieces, right? You can plot points by take your x value, figure which one of the 3 formulas it fits into. Oops, didn't want to do that. And then figure out which one of the 3 intervals it fits into, and then use the corresponding formula. So there's the graph. What's the domain of this? Well, x greater than -4, or -4 comma infinity. The range is a little bit tricky, right? Because the range is the y values. Right? And so we have from 17 down to -2. And then this one starts at whatever y value this is, and then goes up to infinity. So that covers all of these things, right? So this goes up to infinity. But we need to know what is the y value and that's the y value you would get, right? This is the equation y equals x minus 2. It's the y value that you would get if x is actually equal to 1. Right, but we don't actually plug in x equals to 1 into this formula. We have to plug x equals 1 into that formula. So we have an open circle there where y is -1. So the range could be -3, because that's this part. Or it could be any number bigger than -1, because that part goes off to infinity. Okay, so we can graph these things. You have to be a little bit careful about the ranges, because the ranges can be a little goofy. Graphing them is a little tricky, but it's pretty straightforward as long as you keep track of which intervals go with which functions. And then finally, as an example of a piecewise function, think about this kind of a monthly deal: 300 minutes, $20. Each additional time is 5 cents per minute. So what's the function? What's the domain? What's the range? And we've got 2 variables. T is time in minutes. C is cost in dollars, right? So we want to know what the cost is. So up to 300 minutes is $20. So if you use no minutes, it's still $20. If you use 200 minutes, it's still $20. If you use 300 minutes, it's still $20. How much are you charged if it's 310 minutes? Well, that can be broken up into 2 pieces: 300 minutes plus the extra 10 minutes you talked for. That 300 minutes is $20. This 10 minutes is charged at 5 cents a minute, so that's 50 cents. What about 350 minutes? Well, same kind of thing. You need to break that into the 300 minutes, that's $20, plus the extra 50 minutes that you talked for. So that's 20 minutes. 50 minutes at 5 cents a minute is $2.50. So that costs you $22.50. 400 minutes, 300 minutes at $20 plus 100 minutes, that's your whole 400, at 5 cents a minute. And so 100 times 5 cents a minute is $5. So that'll cost you $25. Great, so we can sketch out our graph. This is time in minutes. This is cost in dollars. We usually want to label them with our variables and whatever their units happen to be. And 300 is where our formulas change. Up to 300, it's $20. After 300, it's $20 plus however much, plus whatever overage you've got. So what's the formula? This part, your cost is just $20. This part, your cost is $20 for the first 300 minutes, plus 5 cents for every minute over 300. So the 10 minutes, the 50 minutes, the 100 minutes. So what are these numbers in terms of how much time you used? Well, I take this number and I subtract 300 from it to get the 10 minutes over 300 minutes. This number minus 300 gives me the 50 minutes. This number minus 300 gives me the 100 minutes. So it's however long you talked minus 300. That's what you get charged the extra money for. So what's my cost function actually written as? You pay $20 up to 300 minutes, and then you pay 20 plus 0.05 times t minus 300 for any time over 300 minutes. So what's the domain? Well, like a lot of these functions in word problems, the domain is a little undefined. You can't have negative minutes, so the domain starts at 0. And technically, you can't go past however many minutes there are in a month. But since that's unspecified, we'll just take it to be infinity because we're not going to worry about it too much. The range, the y values start at 20. That's the minimum cost you can have, and they just go up depending on how long you talk. And again, theoretically, that's capped at however many minutes you can talk the entire month. If you talked every minute the entire month, how much would that cost? But we're not interested in that, so we'll just leave it as infinity. So that's piecewise functions.